Hello students, welcome to the video class for the subject Power Electronics and PLC. This subject is for 5th semester Electrical and Electronics Diploma Engineering students. So today our topic is the GTO, Gate Turn-Off Thyristor. So GTO is another type of power semiconductor device. Before this GTO topic, we already covered so many power semiconductor devices like power diode, power BJT, power MOSFET, IGBT, thyristor, diac, triac, etc. So these are all the different types of power. These are all the different types of power semiconductor devices. Also, you can say we covered so many thyristor family members like diac, triac, SCR. So G2 is another thyristor family member power semiconductor device. So today we will cover in this topic what we will cover: its constructional details, its static characteristics, its dynamic characteristics, its gate drive circuit. Okay, so how the GTO is different from thyristor. These are all the key points we will discover under this topic. Okay. So, what is this GTO? Okay, GTO, its full form is Gate Turn Off Thyristor. Gate Turn Off Thyristor is normally, it's like a PNPN device. You already studied in thyristor. The PNPN device structure is like this: P, N, P, N. Okay, so this is anode, this is cathode, this is gate. Anode, cathode, gate. Okay, this is the PNPN structure. So here also GTO has PNPN structure like device. It is a, and it can be turned on like an ordinary thyristor. How the ordinary thyristor will turn on when we apply anode positive with respect to cathode, then the device is in forward blocking mode. So when we apply gate signal, a positive gate signal, then only current from anode to cathode starts flowing, and then the device is in forward conduction mode, and we can say the device is in on state. Okay, so here also GTO also turn on like an ordinary thyristor by a positive gate current. Okay, so these type of devices are mainly like your normal or like your ordinary thyristor, mainly used in inverter circuit, chopper circuit, where the turn-on mechanism is the only gate triggering mechanism. That means in the turn on of the SCR, we will apply positive gate current. And what happens to the turn off mechanism in the inverter and chopper circuit? Thyristor can be turned off by forced commutation. Commutation means it is a turn off turn off mechanism, which I will show you, which we will study in the later chapter. We will cover commutation chapter. Okay, so there are various types of commutations are there: line commutation, forced commutation, okay, natural commutation. So in inverter and chopper circuit, thyristor can be turned off in forced commutation process. Okay, so for conducting for performing force commutation, we need some extra circuitry, some extra elements. Okay, so so to avoid that, for such type of inverter and chopper circuit where the turn on process is like a ordinary thyristor, and the turn off process is by force commutation, in these applications thyristor is replaced by now GTO. Okay, here in these applications GTO is used. Means GTO is more efficiently or more appropriate device. Okay, so GTO means gate turn off thyristor. So it can be easily turned off by negative gate pulse of appropriate amplitude. Okay, so these are the GTO symbol, GTO device symbol. Okay, see, anode, cathode, this is gate. Here two arrow marks are given. One arrow mark is in this direction, one arrow mark is in this direction. Okay, so arrow mark directed towards upward directed, that is for positive gate signal, and the arrow mark represent towards down, that is represented as negative gate pulse. Okay, here also one arrow mark is towards in this direction, one arrow mark towards in this direction. Here also positive and negative both gate signals can applied. This also another type of symbol representation for GTO. Okay, so in GTO it can be turned off by the negative gate pulse of appropriate amplitude. Okay, so GTOs were developed in the time late 1960s, but at that time these devices have not much commercial uses because of its certain type of performance problem. Okay, but in modern technology, but in nowadays this problem is improved, that means its performance issues are improved. That's why now in modern technology GTOs are used in several type of commercial inverters. Okay, so in this case when we are using GTO in place of thyristor, there is no force commutation circuitry. Okay, so that's why when this type of devices can be turned on with the help of positive gate supply and can be turned off with the help of negative gate supply, gate signal, negative gate signal. So that's why the inverters which are used this type of GTOs are mainly compact and cost is also less. Okay, so the negative gate current required to turn off a GTO is quite large in percentage. Okay, so whatever the percentage of current required to turn on this device as compared to this, the percentage of anode current, the gate as compared to the positive gate current value, the negative gate value is much greater. Okay, so the negative gate current required to turn off this GTO, this device, is a large percentage of anode current. Okay, so let's take one example. See here, if your anode current is 800 ampere, if anode current, I will take anode current is 800 ampere, then its negative gate pulse required to turn off the GTO is around 200 ampere, which is 25%. So I told you na that the negative gate pulse required to turn off the GTO is 20 to 30% of the anode current. Okay, so these are the circuit symbol of your GTO. This one you can use any one from these circuit symbol. Okay, so the next part is the static VI characteristics. Okay, so I told you that we covered under this topic its constructional details. Its constructional details is the same as the thyristor construction. It has four layers, three junctions, three terminals, and it require positive gate signal for its turn on process. And the most important difference is that it require negative gate pulse signal to turn off this GTO. Okay, this is the only difference between the ordinary thyristor and the GTO. Okay, so we discuss under this topic its static VI characteristics. This is the static VI characteristics. Okay, so in this static VI characteristics of GTO, what do you see? See, this is the VA axis, anode voltage. This is anode current axis. Okay, see the VI characteristics graph is like this. So what you analyze from this graph, that the latching current for larger power GTO is several amperes as compared to the normal conventional thyristor of same rating. Okay, from these characteristics what you analyze, that for large power GTOs its latching current label is the is higher as compared to the normal SCRs. Okay, so in normal SCRs the latching current level is up to is in between 100 to 500 milliampere, but in case of GTO the latching current level is 2 ampere. Okay, so this 2 ampere is much more greater than the latching level for conventional thyristor. So here the latching current level is 2 ampere. Latching current is the minimum level of anode current required to turn on the SCR or to turn on the GTO. In this case, in this GTO device, latching current level is 2 ampere. Okay, this is the level above which the device goes to the on state, or above which the anode current increases rapidly. Okay, so if the gate current is not able to turn on the GTO, it behaves like a high voltage low gain transistor. Okay, so under this 2 ampere level, below this 2 ampere level, this level, in this level the device is not able to turn on. Okay, so in this level, in this area, the device behaves like a high voltage low gain transistor. Okay, so here see, in a conventional thyristor the latching current level is 100 to 500 milliampere. So here see, we take one average amount of latching current level or gate current level, that is the 200 milliampere. So when Ig, gate current, is less than 200 milliampere, here the device behaves like a transistor, low gain, high voltage low gain transistor. So under this label, this represents transistor operation. Okay, above this, when Ig greater than equal to 200 milliampere, here above this label, in this region the device operates as a SCR. Okay, so when it operates as a transistor, the power loss is very high. When it operates as a SCR, the power loss as compared to this transistor operation is quite low. Okay, so this is the VI characteristics of GTO. Here the different here see, voltage rises towards this direction when we apply gate signal, or when it reaches when the gate current reaches 200 milliampere. In case of SCR operation, it is 200 milliampere range, but in case of GTO, when the gate current reaches 2 ampere range, 2 ampere level, then the voltage decreases and current rises rapidly. Okay, this is the VI characteristics of GTO. So next is the basic gate drive circuit for GTO. So here what we see, where in this diagram what we found, that how the GTO will operate when gate signal is positive, and how the GTO will operate when the gate signal is negative. That means how the GTO turn on and how GTO turn off by this gate drive circuit. Okay, so this is the basic gate drive circuit for GTO. So for turning on purpose, what we do for turning on of a GTO, first what we need to do, first we give the control signal to this TR1, to this transistor 1. When we give the control signal to this transistor 1, this device is turn on. Okay, so when this device is turned on, this switches this TR2 device. Okay, when this device is given control signal, then this device is turned on. When this device is turned on, through this TR2 is turned on or switching to on state. Okay, when TR2 on, And when TR2 is in TR2 means transistor 2 switches to on state. Now this supply voltage is connected to this device through TR2. So once TR2 switches to on state from this voltage supply, from this source, current will flow through this path towards this gate. This is the GTO. This device is GTO. This is anode, this is cathode, this is gate. So once this transistor 2 is switches to on state, current from this source will flow through this TR2. Now taking this path, it will reaches to gate. So the see, gate is connected to the positive terminal of the supply. That means now the gate signal is positive. So a positive gate current will flow through this path. This is the complete path. So when positive gate signal is given to this GTO device, now the GTO is turned on. Okay. So for turning on a GTO, first transistor T1 is turned on, which switches on the transistor T2, and then positive gate current pulse is applied to the GTO, and then GTO is turned on. Okay, so this is the path. This is the path through which positive gate current will flow. Okay, so for turning off the GTO, what we need to do? For turning off the GTO, the turn off circuit should be capable of outputting a high peak current. Okay, so this is the turn off circuit. So what we do to turn off the GTO? The turn off circuit should be capable of outputting a high peak current. Okay, so how this circuit give output of high peak current? For this we need to turn on this circuit. We need to turn on this circuit means what? We need to turn on this T1. Okay, here for the turn off circuit of GTO, one SCR or thyristor is used. Here this is the T1. So for turn off process, for initiating the turn off process, first we need to give gate signal to this T1. Once we getting this thyristor T1 is turned on. So when this T1 is turned on, then this circuit is now completed. When this T1 is turned on, the circuit, and here one voltage source supply, then current will flow in this path. See, this is the path. Okay, clearly visible to you. So once T1 is turned on, then this from this voltage source supply, current will flow through this gate path. How? See, starting from this, it is taking to this cathode, then gate, then through this, then this. So here the direction of current through the gate is towards down, towards cathode to gate. In case of this circuit, current direction is gate to cathode. So here a negative, when this device is turned on, then a negative gate current, a large negative gate current pulse starts flowing through this device and ultimately turn off the GTO. Okay, so this is all about the basic gate drive circuit. So next we will continue with this. We will continue with this topic. Next we will study about the switching characteristics of GTO. Okay, so this is the switching characteristics. Switching characteristics. So under switching characteristics, we will study that the changes occur in the parameters during turn on and turn off process of GTO. Okay, so when the turn on process is going on for GTO, what happens? It is similar to that of conventional thyristor. Okay, so what happens during the turn on process? The Here also GTO is made up of delay time, rise time, and spread time. That means T on consists of three intervals, that is delay time, rise time, spread time. Okay, the turn on process, the switching characteristics for turn on process of GTO is similar to that of the conventional thyristor. So here also the turn on time has three intervals. It is made up of delay time, rise time, and spread time. It's like a similar to the thyristor. So the turn on time. So what are the mechanism, what are the changes in the parameters occur during this delay time, rise time, spread time? You go to the switching characteristics of thyristor during turn on part, and you can study from that part. You can analyze this turn on process, the switching characteristics during turn on for GTO. Okay, so here the turn on time in case of GTO can be decreased by increasing its forward gate current, same as thyristor. So when we increase the forward gate current, the turn on time reduced. Okay, so then next go to the turn off part. Basically here the graph represents all over you. Totally this graph mainly represent you the turn off characteristics. Okay, so before this part where IA is constant, so before this the characteristics is the turn on characteristics, turn on switching characteristics which is similar to that of the conventional thyristor. You can go to that part and study. Okay, so let's come to the gate turn off, the turn off characteristics. Okay, so the turn off characteristics of a GTO is different from SCR. How it different from SCR? Because SCR will turn off by the commutation process or by the turn off circuitry, but in case of GTO it can be turned off by the negative gate signal. Okay, so to initiate the turn off process, GTO carries a steady state IG current. GTO carries a steady state IA current. See, before initiating the turn off process, the GTO is in on state. If the GTO is in on state, that means current rises rapidly in on state and voltage decreases to the minimum value. So here see, before initiating the turn on process, in the C at t equal to 0, here IA is maximum, IA value is capital IA. This is the final value of GTO during turn on time. Okay, so before initiating the turn off process, GTO is an on state, so it carry a steady state anode current, that is steady state on or on state anode current, that is capital IA. So the turn off dynamic characteristics for GTO, what it contains total turn off time. Okay, I can write here total turn off time is TQ. So total turn off time TQ is divided into three intervals, that is storage period TS, fall period TF, and tail period TT. This is storage period, this is fall period, this is tail period. Okay, tail period or tail time. Okay, so let's go to the each time duration each period, storage period, fall period, tail period, one by one. So initiation of turn off process starts. How it will start? So for to initiate the turn off process, we need to apply negative gate current. Okay, so see here ig negative, its graph is like this. So here the negative gate current begins to flow. Okay, so to initiation of turn off process starts as soon as the negative gate current begins to flow. See here negative gate current starts flowing in the negative or reverse direction from t equal to 0 to, so from t equal to 0 ig is now negative. Ig begins to flow in a negative direction or reverse direction. So the rate of rise of this gate current depends upon the gate circuit inductance and the gate voltage applied. Okay, so the rate of rise of this gate current depends upon this gate circuit inductance and the gate voltage applied, whatever gate voltage applied, which I show you in the I already shown you in the previous gate driven circuit, gate drive circuit. Okay, so during this storage period, anode current and anode voltage remains constant. See, this is the storage period from this to this, where ig begins to flow in a, or negative ig begins to flow. Okay, so in this duration, in this storage duration, anode current is constant and anode voltage, this is the voltage graph starting from here. Anode voltage is also here. This anode voltage show you the on state voltage drop. Okay, so here anode current and anode voltage both are remain constant. So termination of the storage period means ending, at the ending of this storage period, it is indicated by fall in anode current and rise in anode voltage. See here anode current falls, anode voltage rises. Okay, so during TS what happens? The extra charges, that means the holes in the P base, are removed by negative gate current and the center junction comes out of saturation. That means during this TS time, the excess charges, whatever excess charges, that means see, this is the layer diagram, this is PN, anode, this is cathode, this is gate, this is J1 junction, J2 junction, J3 junction. So when we want to turn on this device, we need to break this depletion layer at junction J2. So once this depletion layer break down, current can flow through this junction. Okay, so what happens? So when the device remain in on state, the this P, okay, this P layer has maximum charge carriers. That's why the current can flow through this J2 junction. Okay, so when we apply negative gate current, so during this storage period, what happens? The holes present in this P layer are removed by negative gate current and this center junction, this junction comes out of saturation. Okay, so when we turn on this device, this J2 junction reach to its saturation level. Okay, so when we apply negative gate current, the charges means the extra charges which are holes, they are removed by negative gate current and this center junction comes out of saturation. That means it will come below saturation level. So during storage time, the negative gate current rises to a particular value. See, during this storage time, the negative gate current, this is rises up to a particular value. This value is the peak level of Ig. This is the maximum level of gate current, negative gate current. Okay, rises to a particular value and prepares the GTO to turn off by flushing out the stored charge carriers. Okay, so while increasing the gate current up to the peak level, what it does, what it perform in this GTO device, what it is doing, it flushing out the stored charge carriers. Okay, so after TS, what happens? After TS, anode current begins to fall. See, anode current begins to fall and anode voltage begins to rise. Okay, starts rising here. See, so after TS, anode current begins to fall and anode voltage starts rising. The anode current falls to a certain value and then abruptly changes its rate of fall. Okay, see here, anode current falls at a constant slope. This is, so after reaching this value, after reaching certain value, it abruptly changes its rate of fall. See, here the rate of fall is constant, so after reaching certain value, it changes its rate of fall. Okay, here slightly increasing and then again decreasing anode current. So here the rate of fall is changed. Okay, so this interval during which anode current falls rapidly is known as fall time or fall period. So during fall period, anode current falls rapidly, and here the anode current is of the order of 1 microsecond, and the fall period TF is measured from the instant gate current is maximum negative to the instant anode current falls to its tail current. Okay, so here see, current falls at a constant slope. Here the rate of fall of anode current is constant, and at a certain level, and it reach at a certain level, and then it change its rate of fall. So this time, so TF, fall time or fall period, is measured from the instant, you can say from the instant gate current is maximum negative to the instant, this point to the instant where anode current falls to its tail current. Okay, the change of rate of fall of anode current, this point is the tail current level. Okay, so the next is the, what you see at the time t equal to TS plus TF, that means the spread time, the TS means the storage time and the fall time. Spread time is under the turn on mechanism. Here we studied the turn off mechanism. Here TS is the storage. Okay, storage period, TF is the fall period. So at time t equal to TS plus TF, there is a, in from this to this, there is a spike in voltage due to abrupt current change. See, here the rate of fall is remain constant, but here the rate of fall is abruptly changes to another level. So that's why here the rate of rise of voltage is also changes to another level, or here the there is a occurrence of a spike in a voltage level. This is the spike. This is named as spike voltage. So after time TS plus TF, at this level there is a spike in voltage due to abrupt change in current, and after TF, anode current IA and anode voltage BA keep moving towards their turn off values for a time called tail time. This is the tail period or tail time. So during this tail time, what happened to the parameter IA and BA? That means what happened to the parameter anode current and anode voltage? So after this time, after this fall period, the anode current, this is the anode current graph, this is the anode voltage graph. So anode current and anode voltage uh, reach to a reach to another label. Okay, so the anode voltage keep moving towards their turn off values. Okay, this is the turn off value for the voltage, anode voltage. So after time, here current rises, current that means current falls, that means falling rate is another label. Here voltage rises to the turn off label, turn off value. Okay, so after time tt, during this tail time, here the current, anode current termed as tail current. Okay, so after this tail period, anode current reaches zero value. See, after this tt, anode current reaches zero value, and va undergoes a transient overshoot. This is the transient overshoot. va undergoes, so this graph is like at this point. Okay, that means I can draw. Okay, so I can draw like it, like this, like this. Okay, so this, so after this tt, anode current reaches to zero, and anode voltage undergoes a transient overshoot. This is the transient overshoot due to the presence of rs and cs. rs and cs, what is this? In the gate drive circuit, I draw one part like this. This is the r, this is the c. rs, cs, this is gto, anode, cathode, gate. Okay, so after time tt, anode current reaches zero value, and va undergoes a transient overshoot due to the presence of rs and cs. This is, and then stabilized to its offset value, which is equal to vs, which is source voltage, which is vs is the value amount of source voltage applied to the anode circuit. Here rs and cs are the snubber circuit parameter. What is this snubber circuit parameter? We will discuss in the thyristor protection part in later time. Okay, so here you just remember for the time now, rs and cs represents the snubber circuit parameter. Okay, so the turn off process is complete when tail current reaches zero. This is when anode current reaches zero, that means the device is completely in off state. Okay, the overshoot voltage and the tail current can be decreased by increasing the size of cs. Okay, the overshoot voltage, this one, and the tail current, this is tail current, can be decreased by increasing the size of cs, but compromise with the snubber compromise with this snubber circuit loss must be made. Okay, so while we are changing this rs and cs value, there must be happening of some kind of losses, power losses. Okay, so the duration of tt depends upon the device characteristics. Okay, so how much time anode current take to reach this zero level, how much time the anode voltage take to reach this transient overshoot, and then to reach this va is equal to vs constant level. So these all totally, these are all totally depends upon the device characteristics. Okay, so gto has the following, you actually you studied under this gto part. What you studied, you are able to know now the structural details of gto, the static characteristics of gto, the dynamic characteristics or the switching characteristics of gto, what are the characteristics, what are the changes in the parameters occurs during turn on and turn off process. You already, now you are able to know all this. So by studying all these things, now we conclude, now we reach to this point that we can find out some disadvantages of this GTO device as compared to the conventional thyristor. So what are the disadvantages are there? the magnitude of latching and holding current is more in GTO. Already I shown you in the previous part that the here in GTO the latching level is 2 ampere, but in case of thyristor, normal conventional thyristor, the latching level is from 100 to 500 milliampere. So here the magnitude of latching and holding current is more, and here on state voltage drop and the associated loss is also more. Okay, so due to the multi cathode structure of GTO, triggering gate current is higher than that required for conventional SCR. Okay, here also whatever the triggering gate current amplitude or magnitude required to turn on the device is higher as compared to the conventional SCR due to the multi cathode structure of gate. Okay, so multi cathode structure of gate, you already understood that this is like this gate. Here I can apply positive, here also I can apply negative. This is the gate structure in case of GTO. Okay, so gate drive circuit losses are more in case of GTO. Okay, and its reverse voltage blocking capability is less than its forward voltage blocking capability. In case of GTO, its reverse voltage blocking capability is less as compared to the forward voltage blocking capability, but this is no disadvantages as far as inverter circuit are concerned. Okay, so or mainly this type of this device mainly used for the inverter circuit. So when we use this device in inverter circuit, the disadvantages is no more concerned. Which disadvantages? That's its reverse voltage blocking capability is less than the forward voltage blocking capability. So this point is having no concern when this device is used in inverter circuit. So after having all these demerits, this GTO device has some advantages over SCR also. So what are the advantages are there? That GTO has fast switching speed. Okay, GTO has fast switching speed, and its surge current capability is comparable with an SCR. Okay, then it has more di by dt rating at turn on process. Then GTO circuit configuration has lower size and weight as compared to SCR circuit unit, and GTO unit has higher efficiency because an increase in gate drive power loss and on state loss is more than compensated by the elimination of force commutation losses. GTO unit has higher efficiency. Okay, why? Because increase in the gate drive power loss and on state loss is more. Okay, here the gate drive power loss and on state loss is more than the compensated by the elimination of force commutation losses. Okay, that means see, when we use one conventional thyristor, and for turn off of that thyristor we need force commutation process, we need external circuitry. So whatever losses are occur in that force commutation process, those losses are compensated by the gate drive power loss and on state loss which occur in GTO unit. That's why GTO unit has higher efficiency. Okay, then GTO unit has reduced electromagnetic noise, acoustical noise due to elimination of commutation choke. Okay, see, in the commutation process we use certain type of elements like inductor, which we also call it as a choke, commutation choke. So while using commutation choke, there is happening of electromagnetic noise. So in GTO unit there is reduction of acoustical and electromagnetic noises, because here we eliminate this commutation circuit, where here we eliminate this commutation choke. That's why there is reduced acoustical and electromagnetic noise. Okay, so what are the applications of this GTO unit is high performance drive system. Its applications are high performance drive system. Okay, drive system. So what are the circuits under this high performance drive circuit are such as field oriented control scheme used in rolling mills, robotics, machine tools. Okay, rolling mills, robotics, machine tools. Okay, so whatever the field oriented control schemes are used in these rolling mills, robotics, machine tools, these all are used in high performance drive system. Okay, for traction purpose also these type of devices can be used. Okay, and in adjustable frequency inverter drives also GTO is used. Okay, so it's what are its application I already told you. Go through the book and make note of this GTO, make note of this devices, this device characteristics, that means the switching characteristics, the static characteristics, and make note of its advantages, disadvantages, its application. Okay, so at last, GTO's rating. Okay, so what is its rating? Its rating is up to, its voltage rating is up to 2500 volt. This is its voltage rating. Okay, and what is its current rating is about up to 1400 ampere. It is its current rating. So up to this much voltage and up to this much current, GTO ratings are available. Okay, so now you clearly understood details about the GTO. Go through the book and make note of this GTO section. Okay, thank you.